second quantization. Now, we are going to quantize a classical field, and we will see what complications come with classical field. So, let us look at one classical field. There will be lots of classical fields which we will encounter. Well, we did encounter many of them, okay, tons of them in fact. We will focus, well, let us look at several of them in today's class. So, this is Lagrangian for a field which has this is Lagrangian. Given Lagrangian, field theory is fixed, okay. We are not assuming boundaries, boundary is infinite for simplicity. So, this is our in fact, we know this is for string, right, we derived this for string. This was not there V phi, now we are bringing in this V phi, okay, this potential. So, this string is in a potential, okay. So, we will assume a simple potential which is half m squared V phi squared. M is called mass parameter of the field, okay. Now, without this, this is a pure wave equation for a string, right. Rho is mass density, kappa is a constant, okay. So, we can derive Hamiltonian, which I did in the previous classes, and equation of motion. So, equation of motion coming from Lagrange equation of motion, this is definite classical fields. Phi is a field which is function of x and t. So, we get this is the equation. Now, you might have encountered this part, but not m square. Well, you may have encountered, I am not sure, but m squared is the new term which is coming, is mass of the field, mass parameter, okay. Without m, it is a wave which is propagating, no. I mean, in fact, we computed the Green's function and so on. In fact, with m also I have computed Green's function, okay. So, the Green's function for this field in Fourier space, k omega space, it is that. So, k squared coming from Laplacian, d by dt gives you omega, and m comes from here, okay. So, this is the Green's function. Now, this I am sure you can derive it from what I did. Now, from the Hamiltonian, okay, now this is our Hamiltonian, I can write, go to Fourier space, okay. I already wrote the Green's function, but okay, we can just recap. So, phi of x is written as Fourier well, basically phi is written in terms of Fourier coefficients phi k. Phi k is the Fourier amplitude, right, it is the amplitude of the waves, okay. Now, we assume this normalization, and we are assuming the box to be infinite, okay. Now, as I said, you will always encounter not dk, but dk by 2 pi to the power d. D is the dimensional space, which could be 2, 3, 4 as well, okay, 4 in fact higher as well. Now, we can invert it. When you invert it, this phi k is written in terms of phi x, space integral, and so there is a my plus sign here. So, from phi k to phi x, I put a plus sign, and phi x to phi k I put a minus sign. That is my convention, okay. Now, this for phi real is a real field so far. You can do the same thing for momentum. Phi is a momentum of momentum density. So, exactly the same thing. These are real fields, classical fields. So, we can do the Fourier transform, no problem. Now, you can substitute it here. Now, this Hamiltonian density, so total Hamiltonian is integral of Hamiltonian density, or d to the dx in d dimension, okay. So, that is, so I can write down Hamiltonian in the real space, total Hamiltonian, or in Fourier space, okay. Before that, one more thing, the phi is a real field. So, this is a reality condition. So, phi of k and phi of minus k are related, okay. Now, this I will not derive it, I leave it as a homework for you. You can derive that phi of k, phi k star is phi of minus k. So, k and minus k are not independent, and we will see some reflection of it in quantum fields as well. Same thing for pi k, pi is a real momentum, no, I mean, so that also follows this. And please note that this phi amplitude is arbitrary for classical fields, it can be any number, okay. Like for a string, it could be 1 centimeter height, 0.1, there is no quantization of the field in classical physics, okay, but in quantum that will not be the case. And Hamiltonian, this one which is in real space, we can write down in Fourier space. Okay. This is half coming from this half, and this pi squared becomes integral of pi squared becomes pi k pi minus k sum over all k's. This sum is basically I write this sum for convenience, but this is really this integral dk. Okay, this is what you will come always. So, this is quadratic in real space becomes quadratic in Fourier space, okay, but pi k multiplied by pi minus k, or we write as pi k mod square. Okay. This is a Parseval's theorem. Now, similarly for this one, this plus this together, this guy grad square will become k squared, no. So, that is why you get k squared phi k phi minus k. Okay. So, this is coming from the grad phi squared, and the third one is v phi, which is m squared phi k squared. Okay. So, this Hamiltonian, you need to keep this in mind. I am not going to derive it, this I think if is good to derive it yourself. Okay. So, this you should do it yourself. Okay. So, classical field so far. Now, let us go to quantization. Now, this field functions will become operators. Okay. And now, in quantum mechanics we do not have fields. So, quantization of particle motion is called first quantization, right. Electron in a hydrogen atom, when we quantize it, it becomes a wave function. Now, we already have a wave, then when we quantize, what will we get? So, imagine this, we have a this electron wave function is already the psi is there. Now, you need to quantize the psi or electromagnetic field coming from the tube light. So, you quantize that, in fact, we get back particles, in fact, we get lots of particles. Okay. So, the second thing is to quantize fields, for example, QED or like the light coming from the tube light. So, here fields in fact are, you will see that this formalism is not so difficult to grasp. The fields will become fields will give lot of particles. In the field function phi, which we wrote phi of x t, these guys will become operators, which will change with time. But these are operators, these will be matrices or well, these are basically operators, okay, like position operator in oscillator. Okay. So, this called second quantization. First quantization is quantize particle motion, second quantization is quantize the fields. Okay. Field could be Schrodinger wave function itself, which we need to quantize. So, many fields, like in fact, the phi squared field which I wrote few slides back, we can quantize that as well. In fact, we will quantize that field. Okay. So, here we have two types of particles, bosons and fermions. Okay, scalar quantum field. So, presently we will consider scalar particles for simplicity. A photon in fact is not a scalar particle, is a vector particle. It has components. No, photon has spin 1, it has component. So, for simplicity we are going to keep very simple Lagrangian for quantum operator, and I am going to consider bosons first. Now, you see the difference what happens. I mean, this is the formalism is the proofs are difficult, but formalism is not so that difficult. Okay. So, Fourier amplitudes become operators, okay, and these operators will evolve in time, and so this is a Heisenberg picture. In fact, we will not normally deal with a wave function. So, we will lots of particles, n particles, in fact, this particle number keeps changing, right. If you destroy a particle, then wave function, I wrote a wave function for n particles, okay. Imagine like in your usual course, right, n particle wave function, and suddenly one particle has been destroyed or two particles have been destroyed, then what happens to the wave function? It is a problem, no. So, dealing with wave function where number of particles are variable, is not a good framework to work with. So, we work with operators and the number of particles can change in this framework by creation and annihilation operators. Okay. So, this is the thing. So, you make this wave Fourier amplitudes operators. So, we have phi, no, phi I showed you for the string like field. So, we will say phi x t and phi x prime t. Now, this commute. So, this is a commutation, same thing what we do it for quantum mechanics, phi x t operator phi x prime t minus phi x prime t. So, this is different operator, okay. I mean this is this same operator and this a and b, okay, and b minus a b minus b a. So, this phi hat x t. So, it turns out the phi and phi commute. These are two different operators, right? This is at x and this is x prime. So, this is 0, the commute is a postulate, just like commutation relation x p for particles is a I h bar is a postulate. Pi commute, right, position commute for particles, momentum commute for particles, but x and p for particles do not commute. Okay. So, similarly phi, so this is a particle wave function or field and momentum operator for the field. So, that is why momentum operator is very important and we can derive from the Lagrangian this momentum operator. Phi and pi do not commute and the right hand side is I h bar, in 3D it is delta cube x minus x prime. Okay. If they are at the same position, they will become infinite. If they are at different position, they will commute. Okay. So, it is like a particle, particle position and momentum at the same place do not commute. So, that kind of is being captured here. Particle, if you have something is there at the same position, momentum and position do not commute, but if you have the different position, then they commute. But this is not a really particle, this is an operator. Okay. So, these are postulates for our field. Now, this is a real space. Okay. Now, we can go to Fourier space. Okay. I think we need to go slow down a bit. So, is that clear? I mean, we postulate this field operators to the position operators commute, momentum operators commute, but position and momentum operator do not commute, similar to what you do it for particle quantum mechanics. But since this phi is function of x and time, we have phi x and pi x prime. Okay. It was at same time, we are not doing two different time. Now, look at Fourier space. Okay. So, like exactly what we did for classical fields, we can do it for quantum fields. Now, these are operators, but no problem. I am just going to take these operators and multiply by e to the I k dot x. Okay, this is some kind of matrix which is function of k. For every k, we have a phi k. This one I multiply by e to I k dot x and integrate. So, I get phi hat x. Okay. So, you should think of this operator as abstract operator. You do not need to really think what that is. It is an abstract operator. It does something to the states. Okay, and we will define those relations. What does it do to states and what are the states? Okay. So, this is going from Fourier space phi k to real space. We can invert it exactly. Well, by the way, if you know classical field theory, transition is reasonably smooth. You just have to remember this commutation relation and we will find we can work around quite easily. So, from phi hat x, I can go to phi hat k. Okay. Same thing, you just replace these fields by operators. Same thing you do it for pi. Okay, no problem, like that. Okay. I just replace those things by these operators, which are not very well reproduced in PPT, but these are what they are. All right. So, we are Hamiltonian. well, commutation relation, let us do the commutation relation for the Fourier operators. So, we will work with Fourier space very often. Now, Fourier space has shown intrinsic beauty, okay, which I think I am going to mention it bit later, but let us just do the formalism. So, it turns out phi k and so there are like we have x and x prime different positions. Similarly, we have different wave numbers k and k prime. So, phi k and phi k prime, well, irrespective k can be equal to k prime here, field operators commute with each other for different wave numbers. Okay. So, this is well, this postulate you can derive from the phi x. So, either you take the real space postulate or Fourier space postulate, you do not need to assume both, we can derive one from the other. I am going to derive one of them, okay, just give me 1 minute. And so, similarly, one thing is not it should have been here, phi hat k prime, sorry, not pi k prime is also commute, they also commute, momentum operators also commute in Fourier space. But what about position and momentum operators in Fourier space? Okay. So, let us derive it. So, phi k here I write as phi hat x t e to power plus, right, did I make a mistake? No, sorry, minus from x to x to k is minus. So, this is that, this guy and integral gives you phi hat k. Okay. Now, I can't change the color, this one and this one gives you pi k prime hat. Okay. Now, commutation, okay, here product, this is product A B minus B A. So, I can also transfer the commutation here, okay, correct. So, you have to keep this order intact in quantum mechanics, you can't switch it. Classically, we can switch it, but not quantum, right. I mean, this you know from your particle course. So, this commutator I keep it here. Now, I know what this commutator is, phi x prime is a delta function. Okay. So, we put the delta function. So, this one I put it here, I have gotten rid of h bar is 1 for me because you need to carry h bar. So, that is produced here and 2 exponentials. Now, in fact, this is a totally real thing, there is no operator in this, delta function is not an operator, it is a function. Okay. Now, what will it give us? X equal to x prime, I just replace x and x prime equal to x, then what will I get? E to power I minus k plus k prime dot x, integrate this, what do I get? I sitting here, I will get a delta function and this 2 pi will also come, right, 2 pi times delta function, and in 3D is going to be 2 pi cube I k plus k prime, and I forgot this I here, this should be I, the square root of minus 1. Okay. So, this is, you can from real space I can derive Fourier space commutation relations and vice versa. Okay. If you are given these in Fourier space, you can derive the real space, straightforward derivation. Okay.